The last time was on cross product. This is an advanced physics class. If you are new to the channel, kindly share, subscribe, click on the notification bell, and please comment. Now, the very fact that we live in a three-dimensional world, that is, the world is a globe, now explains the fact that people choose different set of axes at different parts of the world. If you live here, you can choose here to be your Y, this to be your X. Somebody who lives here, they choose this to be his or her Y. I'll call that Y prime. Then chooses this to be his or her X. Now I'll call that X prime. So if a vector, say 3, 4, is given to you to plot, and then you do this. Now it means that you are using an axis of this form. But then somebody who chooses this axis may plot that vector in a different way. We are looking at transformation of vectors between different set of axes. Now, the commonest axis chosen by people who live close to the Earth's surface is that they choose vertical to be like so. They mimic it after gravity. Gravity acts vertically. We call this a y-axis. Of course, we mostly walk horizontally, so we choose this to be our x-axis, y, and then sort of x. But someone else may choose a different set of axes, which could be like so. X prime and then y prime. And then their axis may have an angle or make an angle with our chosen axis. An angle, say phi. So then the unit vector in the x direction of the xy plane would be I. Now, of course, for the y you have j. But then the unit vector in the x prime y prime plane, you have I prime and then j prime. How do you transform between these two sets of axes? There is a vector A in both axes, and you could immediately see that the components of the vector in the xy plane will be different from that of the x prime y prime plane. You have this, and then you have that. So for the xy plane, you have the x hitting here and the y hitting there. For the x prime y prime plane, you have x prime hitting here, the y prime sort of hitting here. There are different set of values for the same vector A. So vector A can be written in terms of any of the axes. For the xy plane, you have the magnitude in the x direction, ax, times the unit vector in the x direction, I, and then plus ay, j. But then in the x prime y prime plane, you have vector A to be ax prime, I prime, plus ay prime, j prime. The same vector but different coordinate. So then how can I transform ax prime into ax? So if I'm given ax prime, what should I do to it to get ax? Same as ay prime, what should I do to it to get ay? And we can transform that. So to be able to do that, we need to get I prime in terms of I and j. How do we express I prime in terms of I and then sort of j? So if we isolate I prime from the Cartesian plane, you have I prime like so, and then you have I, and then you have j. Now j is like so, and it can be transformed over here. It can be transferred over here. So this is also J. Then the angle between them is phi. The magnitude of I prime is 1. The magnitude of I is 1. The magnitude of J is also 1. So if we draw the triangle in terms of magnitude, we have 1 here, we have 1 there, then we have 1 here, then we have phi in between. So if you want to analyze I prime, and then we pick here to be 1, let's represent the magnitude of the x with any arbitrary a, and then for the y, let's pick b. We are doing that because if the magnitude of the hypotenuse is 1, the a could be any value, and then the b could also be any value. Of course, this angle is 90. From the Pythagoras theorem, a squared plus b squared is equal to 1. What is a and what is b? Now a could be gotten from cos phi. Cos phi is equal to a over 1. Cos phi is adjacent over hypotenuse. So a is actually cos phi. So depending on the angle between the two axes, then a can take any value. If the angle is 60, cos 60 is half. So a will be half. If the angle is sort of 90, a will be 0. And then b is equal to sine phi. So then we are getting the magnitude of the x component of I prime to be cos phi, and then the y component being sine phi. So I prime, which is a vector, is equal to cos phi is the magnitude, but in which direction? Cos phi in the I direction, so cos phi I plus sine phi in which direction? In the j direction, so j. So vector I prime, which is a unit vector in the x prime direction of the new axis, will be cos phi I plus sine phi j. How do we also get j prime? Now to get j prime, we need to be very cautious. And this angle phi here means that this angle will be 90 minus phi. And if this angle is also 90, then this will also be phi. So if this angle is phi, this is also phi. So if these two axes overlap, they sit on top of each other, and then one of them starts to turn. If the x prime turns a phi angle, the y prime will also turn the same phi angle. So let's express j prime in terms of I and j. So this is j, and this is negative I over here. If this is positive I, this will be negative I. So j prime is equal to, for this component, you have cos phi. In which direction? J. And then in this direction, you have sine phi, but it will be a negative because of pointing at the negative I direction. So sine phi I. So if we rearrange j prime, we have j prime is equal to negative sine phi I plus cos phi j. These two transformations are really important. They would help us to transform any given vector in one axis into a different chosen axis. In the sense that for your newly chosen axis I prime and j prime, which are unit vectors in the x prime and y prime plane, I prime will give you cos phi I. So if you give me I, just multiply by cos phi, and you get the x component of I prime. If you give me j, just multiply by sine phi, and you get the y component of I prime. The same way, j prime will be equal to negative sine phi I plus cos phi j. Right from this, then if you give me ax and then ax prime, which is a vector in the I prime direction. So ax prime vector will be this vector. Would be equal to ax cos phi and then plus ay sine phi. Now this equation mimics this one. If I prime gives us this, then ax prime, which is a vector in the I prime direction, also give you cos phi times, instead of the I you have ax, and instead of the j you have ay. So the magnitude of the vector in the xy plane will be ax ay, but in the x prime y prime plane to give you ax prime ay prime. But then ax prime can be gotten when you are given ax. That will be ax cos phi, where the phi is the angle between the two axes, plus ay sine phi. And then ay prime will be equal to negative ax sine phi and then plus ay cos phi. This is a cos phi, ay cos phi. And let me unbox this one too. They are really important. So the vector A can be written in terms of ax and ay, where you have ax I plus ay j. But in terms of ax prime and ay prime can be gotten when you are given ax, where ax prime is equal to ax cos phi plus ay sine phi. This only for ax prime. This for ax prime in the direction I prime, and then plus ay prime, which is negative ax sine phi plus ay cos phi. In which direction? So this is plus, but this is negative. So plus negative ax sine phi plus ay cos phi, the direction j prime. So if you know the components in the xy plane, and then you have a newly chosen axis, and you want to know the component for the newly chosen axis, just take ax, multiply by cos phi plus ay sine phi, and that will be the magnitude in the I prime direction, the direction of the unit vector in the x prime y prime plane. And for ay prime, you have negative as sine phi plus ay cos phi in the j prime axis direction. So in summary, if you are given a vector A in the xy plane and you want to transform the coordinate into a new given axis, x prime, y prime. Now the vector A could be written in terms of ax and then ay, but it could also be written in terms of ax prime, which is a component in the x prime direction, that is I prime plus ay prime j prime. But you can transform ax into ax prime, and then in other words, you can transform the coordinate over here into ax prime, and then you can also get ay prime from these two. And the transformation goes that ax prime is equal to ax cosine phi plus ay sine phi. And then ay prime, the component in the y prime direction, is equal to negative ax sine phi plus ay cos phi. So just give me ax and ay, and I'll give you ax prime and ay prime. So if the vector in the xy plane is say 3, 4, then you put 3 here, you put 4 here, 3 here, 4 there. And if the angle between the two axes is say 60 degrees, put 60 degrees here, 60 degrees here, and then you get your component in the newly chosen axis. Now we got this equation by first of all transforming I and j into I prime and then j prime. Now I prime is equal to cos phi I plus sine phi j, and then j prime is equal to negative sine phi I plus cos phi j. These are the vectors, the unit vectors in the respective planes. In this case, the I prime and j prime will be gotten from I and j, and the converse of that, if you want to get the magnitude, it also mimics the same equation here. So in place of I, just put the ax, j, put the ay, and the same thing applies for here. So a vector is a quantity. This is a technical definition for vector. A vector is a quantity that transforms this way. It's a quantity such that when you move from one axis to another axis, it transforms this way, where the x component in the newly chosen axis is equal to ax cos phi plus ay sin phi, and ay prime will be equal to negative as sin phi plus ay cos phi. Now the next thing is, how do you get ax if you are rather given ax prime and ay prime? How do you also get ay when you are given ax prime and ay prime? How do we get ax given ax prime and ay prime? We can also find I in terms of I prime and j prime, and then find j in terms of I prime and j prime. But that will be a long process. It can be done from this Cartesian plane. You pick I, then you resolve it into I prime and then j prime. You can do it, but it will be a long process. There's a very short way. In other words, a trick to getting the answer straightforward is by changing the angle to negative phi. So this transformation is such that the angle is positive phi. If you negate phi, it means you are transforming y prime x prime into x and y. You are sending the angle back. So then it is going to be ax prime cos negative phi, but cos negative phi is the same as cos phi. Cos any negative angle is a cos the positive angle. So cos function is an even function, but the sine function is an odd function. So this will give you negative ay prime sine phi. We are getting the negative because if you put negative phi here, sine negative phi is equal to negative sine phi. That's what we have here. And then ay is equal to, so if you put negative phi here to give you negative sine phi, that negative will cancel this. So you have ax sine phi and then plus ay cos phi. If you are given ax and ay, you can simply find ax prime, ay prime with this transformation. If you're also given ax prime and ay prime, with this transformation you can find ax and then ay. So in summary, the coordinate of a vector is not an invariant. It varies from axis to axis. So we can immediately understand that if you are given a vector and then you stand upright and you look at that vector and check the coordinate, it will have a different set of coordinates than when your head is down and your feet are on top. I mean, you stand on your head and you look at that vector, the coordinate would also change. But even in this sort of variant transformation, there is still an invariant, a quantity that will never change. That is, if an observer who chooses an xy plane measures that, he or she will get the same value as an observer who choose an x prime y prime plane. So the invariant quantity is the length of that vector. The length of this vector A in the xy plane will be as squared plus, so the length of A is the squared root of as squared plus ay squared. The same length of A with a newly chosen axis ax prime and then ay prime, we would have ax prime squared plus ay prime squared. And the beauty is that ax squared plus ay squared is equal to ax prime squared plus ay prime squared. You can check that. You can equate these two and then you have this invariant. So the length squared of a vector is an invariant. It doesn't matter who measures it. So you can stand on your head and measure the length of a vector, the magnitude of a vector. Somebody will also stand on the feet. He or she will get the same length of that vector. If it is time to discuss special relativity, you would also observe that in space-time, space is a variant, time is a variant, but there is a quantity called space-time distance. It is an invariant, and Einstein realized that it was a relief that amidst all these variants, there is an invariant, and it doesn't matter who measures it, you get the same value. You can even prove this from the transformation. If you squared ax prime, if you square this quantity, and then square this one, and then add the square of this to that square here, you get ax squared plus ay squared. The cos phi, the sine phi would cancel out. Okay. Now, last in this episode would be the position vector in the xy plane. Now, last time, the position of an object in space and time was analyzed in 1D, and that was a simple case where the position of an object was not resolved in the x and y direction. It is time to talk of the position vector in the 2D and 3D space. So in 2D space, the position of every particle that is in space and then in time is denoted by r. So an object is positioned in the xy plane, and now it is moving in the xy plane. So at a given time t, the position will be like so, and it's a vector r with a length and with a direction. To resolve this vector, of course, you have the component in the x direction, which could be called rx, the unit vector x roof, and then of course ry in the unit vector y roof. Could also call it x roof, then call this y roof. So the position vector r of a vector in 2D space would have a component in the x direction, x roof plus y, then y roof, or xi then plus yj, where the unit vectors can be written as this or that. So the position of an object in 2D space is unlike 1D. The 1D, it had only one magnitude. That was all. But in 2D, it will have two magnitudes in their respective directions, x and then y. Now, in one-dimensional space, the derivative of the position was equal to the velocity, and the derivative of the velocity was equal to acceleration. Now, can we mimic that in 2D? Let's see. So in 2D, if the initial position of an object, let's call that r1. So at a time t1, the object is positioned here, represented by the vector r1 with a component x1 I and then y1 I, y1j. Then the object moves. In other words, the object displaces. It's in motion. So then it moves and it has a second position. Let's call that r2. And it is a vector with a component x2 I and then y2j. Now, what will be a change? What will be the change in the position function? The final position was r2, or it is r2, which is equal to x2 I plus y2j, and then r1 is equal to x1 I and then plus y1j. The change in the position will be r2. Remember the arithmetic of a vector. Vectors can be subtracted. So the final position minus the initial position. Let's see what that gives us, which is equal to a change in r. I'll call that delta r. Is equal to, Let's subtract the x component, of course, x2 minus x1, both pointing in the I direction, plus y2 minus y1. But this is y1, not yi. Both pointed in the j direction. So it turns out that this x2 minus x1 is a change of the position in the x direction, I, plus the change in position in the y direction, j. And you realize this is a vector because of the unit vectors over here. So delta r is also a vector. So the change in position of an object in 2D plane is also a vector. So delta r is equal to delta xi plus delta yj. So the beauty is the change in position is a vector, and it is equal to the magnitude of the change in the x direction, I, plus the magnitude in the y direction, j. And let me unbox this. So delta r, the change in the position function, which is a vector now, is delta xi plus delta yj. So this vector here represents the change of the position function, delta r. So the object was originally here. Then it moved to this position. The delta r represents that change. And delta r is also a vector, which is delta x. This represents the delta x in the I direction, and then delta y in the j direction. That is a vector, kind of, delta y, j. That is a vector, delta r. So it has a change in x and a change in y. Let's put this equation down. Delta r is equal to delta x I plus delta y j. So given a change in the position function, then we ask ourselves, can we cook other vectors from this change in position function? Yes, we can. How do we cook that? Now, the position of an object changes with time. So maybe we can divide by time. And we can divide by time because time in this case is a scalar. Now, in non-relativistic mechanics, time is a scalar. But in a relativistic mechanics, time will be a vector. Now here the speeds are so not comparable to the speed of light. For that matter, and time can be treated as a scalar and not a vector. So if we divide through by delta t, that is a change in time. The time the object took to move from this point to that point. And we are getting this to be a velocity vector is equal to the velocity in the x direction, I, plus the velocity in the y direction, j. So if an object moves in a 2D plane, the net velocity, which is a vector now, is the sum of the components in the x direction and in the y direction. So each of them can be treated differently. For the infinitesimal case, so say if the change in the position is such as this, very minute, infinitesimal. So the change in the x is so, and the change in y is like so. And it turns out that dividing by delta t, for the infinitesimal case, you are going to get v to be equal to dr the t, and you have here to be dx dt instead of delta s over delta t if it is infinitesimal change. So times I plus dy dt times j. So the derivative of the position vector is also a vector. It is a velocity vector of the form vxi plus vyj. So then it also turns out that the derivative of the velocity vector will also give you the acceleration vector. So dv dt dv dt, we're able to do this because time is a scalar, is equal to the vx dt in the I direction plus the vy dt in the j direction. But this is the overall acceleration in the 2D plane. It's a vector. That vector has x component, then a y component. For the x, you have the vs dt, which is ax, acceleration in the x direction, I, plus the acceleration in the j direction, sort of ay, j. So, if a particle or an object moves in the 2D plane, the change in position or the displacement of the particle is a vector, delta r, which can be expressed as a change in the x times I plus a change in the y times j. Then the derivative of that position will also be a vector, velocity, which will be the velocity in the x direction times I plus the velocity in the y direction times j. And the derivative of the velocity also gives you an acceleration vector, which is the acceleration in the x direction I plus acceleration in the y direction j. So the beauty of these equations are such that in 2D plane, the objects can be analyzed in both components separately, because the acceleration of the x component is different from the acceleration in the y component or in the y direction. So if the acceleration in the x direction is a constant, that is, if ax is a constant, then the kinematic equations will be written in terms of ax and it will hold. Then you write a separate one for ay and that one too will hold. So let's conclude the episode by writing the new kinematic equations put forward by Newton as vectors. So the first was a position function, and in one dimension it was x of t, and now it is going to be r of t, which is a vector, is equal to initial position r naught, which is a vector now. So it has an x component and then a y component, then plus v naught, the initial velocity, which is a vector now, times t. T is not a vector, it is a scalar in non-relativistic physics. Then plus half, now a is a vector now, and then t squared. So then you can sort of split this equation into two, one in the x component and a y, sort of one in the y component. So it turns out the velocity, which is a second kinematic equation, is going to be the v naught, which is a vector now, then plus a, which is a vector, times a scalar t. Then last of all, we have v squared, which is a vector now, is equal to v naught squared which is also a vector, plus 2 the acceleration, which is a vector, times delta r, which is also a vector. So these are the three kinematic equations put forward by Newton as vectors. And the beauty of these equations is that you can split them. So if you want the x component, just write there x of t is equal to x naught plus v naught or vx naught t plus half axt squared. If you want the y, then do same. Thank you for watching this episode. The next episode would be projectile. Projectile motion is going to be a motion which will encapsulate all these ones. In other words, in projectile motion, the position of the object is a vector, both in the y and then in the x. You launch an object, and at every moment in time, it will be a vector. The position will be a vector. You have a y component and then the x component. And we are going to use these equations. And thank God we can split them into x and y separately and analyze the object and draw conclusions. This is an advanced physics class. Kindly subscribe, share, comment, click on the notification bell. Please do well to share.